think have recording working. Hopefully. Good morning. Is there anybody still on the wait list? I mean, I have no idea. Okay. I know that things keep moving. So there were a couple of questions. I thought I would try to address them first. One was, why are we reading all this stuff, this database stuff? And the motivation for this is, as we move through this course, we are going to be talking about two things that directly tie into databases. Number one, and probably the most important, is how do I recover from failure? If I give you a black box and I say it's broken, how are you going to fix it? I don't know. Exactly. I don't know. The first thing you're going to do is take a crowbar out and, yank the top off and start looking inside. So what I'm doing is giving you the Chilton's manual for this black box, the database. Now, if you've already taken a database course, then that's not going to be very interesting. How many of you have taken 404? All right, so like 20% of the class. So that's going to be pretty light reading for you because it's basically what you would learn in 404. The difference is I'm not trying to teach you how to build a database. I'm trying to teach you to understand just enough about it so that when things go haywire, you can figure out how to fix them. The other question was, what am I supposed to do this week for the capstone? This is the early part. This is the part where you should start exploring. You have the freedom to not say, oh my God, this is due in 2 days, I better actually do something. So start thinking about it. Why did you take this class in the first place? Well, because I heard it was an easy class and I wanted to get a good grade. Or I heard that this makes it easier for me to find a job. But it only makes it easier for you to keep the job if you actually learn what we're talking about in here. So part of that is understanding what problem distributed systems solve. There's a huge space of these. It's not like you're going to sit down and enumerate them on the fingers of one hand or two hands, or even if you take off your shoes and use your toes. So start looking. You're not under any stress yet. There's no pressure. Now is the time to explore. It's time to say, what could I do with this? If you just simply want to keep it really simple, you say, I just want to build a simple mechanism for replicating my MySQL database or whatever. It doesn't matter. I want to build a MapReduce because, for whatever reason, people like MapReduce. Or maybe your interest is very much in machine learning, at which point then you're going to want to start to understand how you replicate graphs and how you maintain coherency across them and how you deal with failure. I haven't forgotten going to a workshop about 25 years ago, which was the Scalable Global Parallel File Systems workshop. And the kinds of people who went there were people who work for very secretive agencies. And one of them wanted to know mostly about how they could manage trillions of 512-byte files. Turns out that fits the metadata of a typical phone connection. So somebody who was looking at large quantities of phone data, and they wanted to analyze that. But one of the things I remember from that particular workshop was a group had built a cluster of 128 Sun workstations. Yeah, this is 25 years ago, so Sun was still around. Now it's called Oracle. A group had built a single cluster of 128 loosely coupled Sun machine systems, each with 40 storage units attached to it. And the longest amount of time they had been able to get it to run entirely run was 18 minutes. This is what happens as we start to scale up systems. You can talk about 99.999% uptimes, but what that means is, what is it, 5 minutes per year or 12 minutes per year? That each individual component is allowed to be down. Okay, well, that doesn't sound like a lot until you have 100,000 components. Have any of you ever heard of Amazon Web Services? And the person who used to be here at UBC that I came here to study with and then he quit and went to Amazon actually works on S3. And S3 is in fact it's a distributed database at this point. They actually just announced a few weeks ago that they've implemented strong consistency. It used to be weak consistency. It used to be an eventually consistent system. What's the difference? Well, I can tell you building a strongly consistent replicated database is a lot harder to do without destroying performance than a weakly replicated one. Amazon actually buys storage devices. They buy disk drives, they buy NVMEs as well, but they buy a lot of disk drives. Why would you buy a disk drive instead of buying a solid state drive? It's a price issue. How many of you know that non-volatile memory devices actually wear out? I've actually seen storage that wears out when you read it. I've had to model that. I've had to look at it. It's like, wow, that's kind of a weird sort of problem. What do I do when one of those devices wears out? How do I actually handle that? And guess what? Now you're back into the database conversation. The same techniques we end up using in databases are used in low-level storage devices. So we see these patterns happen over and over again. So use this time to explore. Ask yourself, that's pretty cool. If I take min.io, how could I actually get that to be strongly consistent? And if you don't know what min.io is a local implementation of the S3 interface. So that's something simple, something interesting. Or you could be really ambitious and go, yeah, I got this great idea. I'm going to build a, blah, 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 whatever. I was thinking about it on the way in. I was saying, hey, wouldn't it be kind of cool if I could actually have my own captive chatbot so I can talk to my own AI and know that the data is not actually going to someone who's going to then use it or leak it? Of course, data leaks don't happen, so you don't have to worry about that, right? Anybody ever use ChatGPT? Turns out that every conversation with ChatGPT, including conversations that were deleted, are going to be provided to third parties as part of litigation. So what you share with an AI, a public-facing AI, is not secret. So there's a reason, a motivation for why you might actually want to build one of these on your own. And then it's like, what are the robustness issues there? What does it mean when I start sending messages and they don't go through? How do I handle that? It's not a great distributed systems topic, but it's at least one. Okay. Why are we not moving forward? So, here's where we're going to start today. If two events are concurrent, what does it mean to say one happened before the other? I mean, we're actually in an engineering building, so maybe it's not quite physics, but it's getting closer to physics than computer science is. And I will tell you that physics actually really teaches people now the kind of shit you're like, this can't possibly be the real world we live in. So how do we tell?
I was going to say, in your frame of reference, you see one event happen and then the other happen.
What's the fastest that you can travel? Yeah, but there's a lie underneath that, which is light doesn't actually move. That's the part that really plays with your head. start talking about causality in the real universe, it doesn't work the way that you think it does. And a lot of that is because we actually are the outlier in the way that the universe appears to be organized from everything we can tell right now, where the universe is mostly about potential, and that potential only collapses to something finite when it's observed. Now you're sitting there going, but wait a minute, I keep observing things over and over again. Yes, that's what makes you the deviant. I mean, I've actually seen theories as crazy as the fact that there might only be a single electron in the entire universe. You're like, wow. But what does it tie back into here? It ties back into this point that we start talking about observer frameworks and reference points and whatnot, and we use these to orient ourselves relative to the manifold that we are operating in, and we say, it depends. See, this is what makes distributed systems actually hard. The time that it takes, if time exists, we'll pretend it does, the time it takes for a piece of memory in your CPU to be read. Anybody know what that is? Ballpark? It's about 500 picoseconds. The CPU also has a cache on it. It's the same kind of memory, actually. It turns out 500 picoseconds. And then it has another part of cache. And when you go look at modern dies, almost all of the CPU is actually level 2 cache. Do you know how long, roughly, again, average, because these timing haven't changed very much lately, roughly what the access time is to level 2 cache? It's about 7 nanoseconds, more or less. 500 picoseconds to 7 nanoseconds is a 14x difference. So the things that you observe when you're 500 picoseconds away from something are different than the things that you observe when you're 7 nanoseconds away from something. And we're still at nanoseconds, right? So the differences are small, but they are there. So as we move further and further away, and the distance required to even communicate gets larger and larger, our frames of reference diverge, and it makes it more difficult for us to understand a common sense of what time is it. And then we get screwy things like general relativity, which throw in the fact that gravity kind of screws with time. How many of you have a smartphone? And the people who didn't raise their hand, how many of you are lying? Right, exactly. The point is, okay, so all of these phones, all these devices actually have GPS capabilities built into them these days. Why is that really important? There's many possible answers here, so just pick one.
Maps.
Sorry?
Maps.
Maps, for maps. Okay. I could knock the M off and it would still work. Right, so maps are one example. Maps need to know exactly where you are within 10 meters or less. Apps need to know where you are so they can keep track of what ads to show you. That's why I said it could be maps or apps. One of those is useful to you. Well, maybe both of them are. Maybe you really want to get relevant advertising because, hey, I just finished 416. It's 12:50. I'm hungry. And it's going to show me the places nearby I can go eat. Great. The GPS satellites, the things that we actually use in order to coordinate, to triangulate our location on the Earth, actually do experience relativistic effects in their clocks. And we were correct for it. There are places on the face of the Earth where gravity is slightly below the average in other places, or probably slightly above, because it's an average. And time actually does travel at a slightly different rate there. So, simultaneity, the idea that two things happen at the same time, they're concurrent, is difficult for us to reconcile. And they're not just academic exercises in distributed systems. They're real hard problems in distributed systems because if I want consistency, I need to guarantee that these events only are visible both or not at all when I have two of them and I'm trying to coordinate. So when I start trying to replicate databases, what I'm actually doing is saying, how do I make sure that the updates appear to be applied simultaneously? We don't have real simultaneity. We have to simulate it. We have to come up with a way of agreeing that we can order things in such a fashion. Yeah, the mouse is working. It's just not working. Probably would help if I plugged in the USB. There's always something. Okay, so let's walk through some ideas. How about we use the receiver's clock? So we have node 1 sends message 1 to, I guess in this case, node 3. Node 3 receives the messages from node 1 and node 2. Okay, node 1 and 2 both send them. Node 3 receives the messages. If node 1 and node 2, let's suppose we actually were able to sit above this as some sort of a godlike creature and say, those were sent at exactly the same time. What guarantees do we have that they will be received at exactly the same time? Why not? I see lots of people shaking their head and somebody going, oh yeah, of course it's going to. Why not? I mean, we don't even have to get into the sense of time. We have a structural issue here. Those messages are going to show up in a queue. So one of them will be earlier in the queue than the other. That's just structural. We don't even need to have a skew of the time. So node 3 is likely going to define this based upon its own clock. It's going to say, I got this at this time. I got this other one at this time. And they're going to differ, assuming we have enough granularity in the clock. So this is one possible way of dealing with it. Actually, maybe this works now. It does work. We have network delays that aren't constant. That's actually even worse than the structural one. Well, it's different than the structural one, so it's another reason why we can't control the order of the messages arriving. So if we have two messages that were sent at different times, there's no guarantee that they arrive in that relative order. So they could arrive out of order. See, once we start talking about things like GPS, we do in fact get into this interesting world where the propagation delay becomes an issue. So the time it takes for you to get a message between your laptop and your phone is likely very short because you probably keep them next to each other most of the time. But then you use a computer that happens to be in Arlington, Virginia, because it's at one of the Amazon data centers there. It's just going to take more time. And so the order of events won't be the same. So the receiver isn't going to see the messages in the order they were sent. It can only see the order in which they were received. So the receiver's clock doesn't define the causal order of the actual events. So that wasn't really the right solution. So now let's use the sender's clock. So we put a timestamp in the packet, and we send the message, and the message arrives. And now we've got these timestamps. OK, well, that's great, but what does it assume? Synchronized clocks. There is a really interesting piece of work that Google did where they actually put atomic clocks in all their data centers, which at the time was like $500,000 each. You can now do it for under $5,000. And that will allow you to have clocks that are synchronized within some epsilon band. You're not guaranteed they're exactly right, but what you are guaranteed is they're no more than this much different. And they said, OK, well, all I have to do then to guarantee that the order is always preserved is hold the packets for the epsilon band. So you always make sure that the packets aren't processed until after they've waited long enough that everything has arrived. It's kind of screwy, but that requires that you have synchronized clocks. And synchronizing clocks becomes more complicated as distances go up. So last time, I think it was last time, one of the times I taught 416, I talked about, because I find it's a very useful way to make it easier for people to think about this. It doesn't really change the problem, it just changes the scale of the problem, so it makes more sense intuitively. Let's suppose we're building a lunar data center. Does anyone know the approximate time of a message to get from the surface of the Earth to the surface of the moon? It's about a second. So it takes about 2 seconds to get back. Anybody know what the time is to get to Mars? That one's fun, because it varies sometime between around 2 hours and 20 minutes and 22 minutes. because the relative position of the Earth and Mars is constantly changing. Trying to get your clock synchronized there gets really hard. As the distances go up, the variation in time goes up, the ability to keep your clock synchronized gets more challenging. There's a really cool XKCD that shows, the modern internet, and in the bottom right-hand corner, there's this one supporting strut that says that, one guy maintains this piece that holds up the internet. That's NTP, the Network Time Protocol. The Network Time Protocol was developed in the late 1980s by an academic at University of Maryland, if I remember right. Could be wrong there, though. I just remember the name of the machine he was doing this on was called Fuzzball. Why I remember that? I don't know. The NTP protocol works by evaluating what the jitter is in the round trip times and using that to then adjust clocks between computers. It's not the fine accuracy that Google gets with I think, Spanner. It's a little coarser than that, but it's pretty good. It's usually within about 10 milliseconds, and 10 milliseconds is good enough for a lot of ordinary uses. And we actually use this kind of mechanism. As long as you can live with the variation there, this level of global clock definition is workable. But this is definitely bounded by the communications time, by the time it takes, the variation. So I just gave you the Martian example. And the Martian example means that now you've got to hold up every packet for 2 hours and 22 minutes. That's what we'll put it on a blockchain, which is only an hour, right? Anybody heard of Bitcoin? So Bitcoin transactions take about an hour before they become computationally impossible to change. The history hardens at that point, and it's no longer considered to be feasible. That might change. So we can't really use sender timestamps to define a causal ordering. So reasons this doesn't work: clocks drift. We have oscillators that are imperfect, and we can adjust them somewhat, but we always have some variation there. Google Spanner is the one that tried the universal global clock, which is a cool trick. So we can't assume that physical time really exists. We can assume that each individual node has a sense of its physical time, but we can't correlate them across the instances. So how would we be able to solve this? Well, if we could capture ordering without having synchronized clocks, that would be really cool. Is there a way to do this? And what would we need to do? Do nodes need to agree on global time? We went to that solution initially because it's easy. But nothing in distributed systems ends up being easy. This is what makes it difficult. So what could we do instead? Are message delivery times fixed? Are they variable within a bound? Are they unbounded? That one really makes a huge difference, because one of the key findings that came out in a paper in the 1980s, 1985, it's not a particularly long paper, and we will touch on it soon. I don't remember exactly when it shows up. It's called Floyd Lynch-Patterson, named after the three authors. And the observation was that in a distributed system of n nodes with unbounded message delay, you can't guarantee liveness. In other words, you will never be able to recover from the failure of a single node. And the intuitive reason is because you can't distinguish between failed node in a system with unbounded message delays and a non-failing node where the message just keeps getting kicked down farther and farther and farther, so it takes longer and longer to arrive. And this was kind of a bummer, right? Except that it didn't actually mean that we couldn't build distributed systems. What it meant was we couldn't build them under the model that we can fix everything. That's why we have to understand, what is our model? What are we actually doing? What are the limitations of our model? What are the things that we say we must have in order to be able to fix them? This is why I start with failure. I say, this is the failure. How are we going to fix that? And by identifying the map from failed state to running state, we can build up our list of things we need. These are the guarantees we need from the system. These are the invariants of the system. And we're going to use those invariants then to define the system that we construct, and more importantly, the protocol we use to guarantee that when things go wrong, we can recover from them. Now, the other way of presenting this, and the way that it's typically presented, is people give you the protocol first, and then they work backwards from the protocol to show you how it solves the problem. And that's great, but I don't think it connects as well as if we start with a problem and say, how do we solve that? How do we get back to a system that works? A simple example of this: suppose that you actually have a cluster of replicated database instances, and one of them suffers a drive failure. That couldn't possibly happen, right? Hard drives don't ever fail. NVMe doesn't fail. Power supplies don't fail. I like the storage failure because the storage failure is the hardest of those things to recover from. The IT people come in, they diagnose the drive is dead, they replace the drive. Now you have a database with an uninitialized drive. They initialize the drive, they recreate the database, and the very first thing it does is it comes up and it starts running the replication protocol, and the first thing it says is, we need to elect a new leader. And it wins the election. What? What does its database look like relative to all of the other copies of the database? Probably a little sparse. It's an uninitialized, well, it's a newly initialized database instance. It has no data in the database. So even though it was elected as the leader, it doesn't actually have any of the data, so we can't allow it to answer any questions. In fact, we can't allow anybody to make changes to the database until we've recovered the leader's state. But we started with a failure, and we worked backwards from that. And that's going to end up leading us into the protocol that we'll be talking about a little later, which is going to be the Paxos protocol. Do we need to have a global time? I'm going to argue that we don't, but we're going to need something that allows us to reason about the order in which things occurred. Message delivery time almost always has to be bounded, because otherwise you're going to run into FLP. You're going to find out that you can't solve the problem, because you've generalized this. But you can pick things here. In the RAF protocol, they pick 150 milliseconds as a bounded time. Why is 150 milliseconds always the right answer? It's not. Great. This is why I ask questions, because, of course, an LLM would lie to you and try to come up with some bullshit answer that says this is why. And then that's how I can tell they're lying. But it's okay to say that doesn't work. It's not. It's an arbitrary choice. It was a specific choice they made relative to the model they were trying to support. Can the network experience failures? Absolutely. Anybody who's ever used any computer on a network knows that sometimes networks fail. How many of you actually play, I don't know, video games, like online video games? Like, are they adversarial online video games? You know, you try to kill them, they try to kill you. First-person shooters, anything like that. And what happens when something goes wrong with the network? You die. The network repairs, and you're dead. And you persist at it, and you restart, and you try again, because it's a game. So of course that's going to experience failures. We are always going to be recluded into the network failing case because we know that that is a predominant source of the failures we're going to see. I picked the hard drive failure case because it's the one where you might have said, I never thought so about hardware itself failing, but it does. Could be malicious nodes. This is a fun one. What does it mean to be a malicious node? A compromised node that might be lying about something. Does it have to be lying? Lying implies intent.
It could be
Unwillingly lying. Go back to our computer then. Okay. Common hardware. Flip hits. Partially truncated messages. We protect some of those things because we put checksums on them. And checks solve all world's problems, except when they don't. Do hard drives ever lie? It's a binary question. You don't really have to think so hard about it. You're just afraid of being wrong. Yes? There was this fascinating presentation at Microsoft that I was trying to remember. It was a conversation I had, an actual talk I attended, but they had three groups at Microsoft who were building robust database systems. One was the SQL Server team, one was the NCFS team, and one was the Exchange team. And the Exchange team specifically talked about how they noticed that sometimes when they read data back from the drive, it didn't come back the way they wrote it. And they detected because they were adding checksums to data. They were doing a whole end-to-end thing. It turned out simple people in the NCFS people weren't doing that. So they weren't seeing those errors. So then when added the checksums, they found, lo and behold, there's a non-zero chance that the drive will just return data different than what you think should be there. Is that malicious? It might as well be. From our perspective, it doesn't matter. Usually the term that we use when we discuss is Byzantine. It's wrong. It doesn't necessarily have to be deliberately wrong. But the deliberately wrong case, the malicious case where someone is actively trying to subvert the system is also possible. And we will discuss how to deal with that particular class of failures. That's when we start talking about Byzantine failures and recover from Byzantine failures, then you're towards the end of your trip into the systems. Well, I mean, it's a very long trip. Probably back in office and part before it's done. Because fixing and resolving and recovering from Byzantine failures is possible, but it's complicated. One protocol that does this is the blockchain protocol. Another way of doing this is instead of thinking of time as being an absolute value, we can think of it as being a relative value. In essence, a monotonically increasing value can act as a form of clock because all we care about is ordering. Anybody here have a math background? You might actually remember that ordering is in fact a property that fucks us over in mathematics because the moment you have to consider the axiom choice in systems, it gives you really weird results. So ordering in some domains is just really, it's easily conceptualized, and then you look at what it actually means in the world of math. You know the axiom choice? Okay. And you know how it screws up math. Because it's one of the classic examples of contains there. You can either prove it or disprove it within the axiomatic set theory. And you integrate math systems to add it to the system or add its nation to the system. Pretty cool. But anyway, the point here is we're not actually bound to that in this instance because we're already living in a finite world, so we're not worried about the infinite problem. We talk about a finite problem. Can you think of anything in networking that uses a logical clock? Yeah, that's all they are. Sequence numbers are nothing more than a logical clock. Now, the way we make an infinite one logical clock is we treat things around the minus 1 to 0, or all 1s to 0 flip. We treat that specially. So we keep the window smaller, so we can always get back when you overflow the bits and then start counting back to 0 again. So logical time just captures causality. It's not actually a timestamp. It's a logical sequence number that allows us to reason about the order in which things occurred. This doesn't require synchronous clocks. It has to be strictly increasing, although I already told you I can flesh that when you have a finite number of bits. And you can use it to reason about the ordering of events. So this is how computer science gets around the axiom choice, which is simply the choices. So, in 1928, Leftward, Leslie Leftward, who you will hear his name over and over again because he gave us the big router in 1974, he gave us logical clocks in 1978, and he gave us Paxos in 1998, although the paper was submitted in 1991. It was so complicated, it was actually very simple, it's easy, but it didn't work very well for the brains of computer science people reading it, that we didn't publish it until 98. And we're going to talk about Paxos, and you're going to actually get to design a Paxos implementation later in the course. And that's Leftward. And then we're going to talk about PLA Plus at some point, and PLA Plus was created by Leslie Leftward. Have you heard of LaTeX? La is for Leftward, because Alton News built tech, and then Leslie Leftward built a macro package on top of tech, and then we have Leftward, tech, or LaTeX, or LaTeX, depending on how you want to pronounce it. If A and B are events in the same process and A comes before B, then we say A happens before B. If A is ascendant and B is the corresponding C, then A happens before B. Transitivity. If A happens before B and B happens before C, then A happens before C. Well, the mathematician is really stressing out, isn't it? Because it's like the first A. Concurrency means if A is concurrent to B, if and only if neither A happens before B nor B happens before A. In other words, it's time determinate. It doesn't fit very well in, binary systems. Concurrent events don't have a causal relationship, so they don't influence each other. They are truly independent, and reasoning about their ordering is more challenging. So let's take an example of a concurrent event. Where we have three processes, process 1, process 2, process 3. We have messages they emit, and you can see that the two messages from process 1 and 2 are sent at the same time, arrive in different order than they were sent, because, like I said, there's 2 somewhere, and that always works in order, and then we can see the response, the E3, M3. So part of what we're doing here now is saying E3, M3, which is a message, the third message, is labeled in such a way that we can tell that it has a happens after, or we always say E3 happened before E1, M1, or E1 happened for E3, E2 happened for E3, even though we can't say the order in E1, L1, or E2, M2 happened. Since the only nature of the current, they didn't have a causal linkage. E2 to E3, on the other hand, has ordered operation because the receive and the send are ordered. And the same thing for E1, E3. But here's the interesting thing. The two messages coming in has one message going out. Order reliable doesn't matter. I mean, the mathematicians are well versed in what lattice is. It's a very useful structure. It's a mathematical structure. It's a very useful mathematical structure when we start talking about distributed systems because it allows us to reason about these things by saying, you know, maybe the order in which they happen doesn't matter because the result is the same. This is what we call isomorphism. It's not identical, but nice or effectively we can substitute one for the other without changing our analysis. So 9 clocks, every process has a counter. The counter says each new event, each value counter is just simply incremental on the previous value. That doesn't say +1, it actually doesn't have to be exactly 1, it just has to always be increasing. You can make it 2 if you want to, or you can do it between 1 and 3, it doesn't make a difference. So you can throw them away. In essence, you can say, well, I didn't use our value, it doesn't matter to the analysis. And I know that because there are many times when we do end up throwing them away. So when we send a message, we increment our counter, and we attach the value of our counter to the message. Now when we get the message, we receive a timestamp that contains a vector of all the counters. I was looking at that. And the way that this is usually actually implemented is we have a vector, and each entry in the vector corresponds to one of the nodes that's involved in this particular communication, so that we don't necessarily know exactly how things flow through the system, but we can reason about the order of events within isomorphism to how things happen. And this is a lot harder to think about than simple causal time. But we'll keep working through it, and eventually we'll get to okay, I can see that. I don't have to worry about how the innards were implemented. I just have to worry about this is what came in, this is what came out. The fact that there are 4,700 different ways it could have gone through those transitions doesn't matter to me. So the key property here is that for a message, if A came before B, then the timestamp, the counter value of A has to be less than the counter value of B. But the reverse is necessarily true. Because the counter value of A less than the counter value of B doesn't mean that A came before B. They just simply mean concurrent. So a simple example of this. We watch the flow of the counters going through here. So you can see the message comes from process 1, process 2, to 3, then we generate a response in process 3, and then process 4 send a message here. Back to process 1, send a message to process 2. So process 2's clock increases 1 to 3 because it is 1, this one is 2, it has to jump to 3. It has to be strictly greater than 1. This is actually not a clock yet, this is just a story clock. We need to reason about. I think I have myself. We'll get to the clocks because they are fun. This is a simple clock. It's one integer process, it provides total order, and what it does is it allows us to logs to together and construct an order of events in those logs. Turns out that building distributed logs and putting them back together is a whole research area. One of the faculty in CS, there's no one in this area. He's on USD 16 back. He hasn't talked a while. The meaning of this is you can't distinguish causality from concurrency. So what do we need? Well, what we need is what I was trying to jump to pretty earlier, which is a vector clock. So what we need here now is we have the fuzzy lattice thing going on, where we do the vector, and each slide in the vector corresponds to the process from which it came from and the counter that we last seen from that process. And this becomes essentially a snapshot. What do I know about everybody else's progress? So the rules for this are, when we're talking about local events on node I, the value of the vector I is incremented by 1. That's my counter, my local counter. When I send a message, I increment my local counter and I attach my entire vector, everything I see from everyone else, to what my counter is now I incremented. And this is what's going to create that more rich vector clock. To receive messages with a message, and now we can actually reason about them by just simply taking maps of what we've seen, and maps of and value of whatever the input message is seen. So in other words, it becomes a way of saying, I had thought that node in 2 weeks, we probably yesterday. So now I'm going to update the last time I've interacted with it indirectly is yesterday, because that's what's in your counter for. So this is always increasing. It's always guaranteed to one quantity increase. This is the ordering. That's the whole point of it. That's what we're trying to achieve. So here's a more detailed example of what a vector clock looks like. I'm not going to spend too much time walking through this because I don't think it's going to be clear. The more planning and seeding in your brain. If you feel comfortable with vector clocks, right? If you don't feel comfortable with vector clocks, questions, go watch a video. Or maybe not a video person, go read some papers. Do that too. Ask God, ChatGPT, or Graph. Graph Onion might not be as useful though. I have no idea what Graph Onion is, ask that. And now we have vector clock. Comparison is kind of difficult because we can only say something. We can only say something that's not equal to every individual counter in the vector is less than every other counter in the other vector. Although it's kind of like not directly related. We don't know what the order of events here was. And the not, they're just less than. If only if you let's see. If the A is less than DV, I think that's misnotated. I think the A is Y less than equal to Y. There we go. All right. So P is like is A plus equal to B, even only if the vector A is strictly less than the vector B. A is concurrently B, even only if neither of those vectors are less than the other. So for example, if 2 over 1 4 1, we can't run any inference about ordering of the events in this particular case. So this is what's going to make this thing lattice. Because in essence, the closest sort of concurrent, this is what we can't reason about them. What we're going to look for is where are the boundaries before or after that, where we can start reasoning about them. Anything in between there, you have to go, I don't know what the order is. So the vector clock is actually concurrency. It's not just about ordering. But vector clock row decides the number of nodes involved. Because necessary full vector large and sparse vector implementations you can use. And adding new members of the vector become increasingly complicated. So if you think about this, the general case of this would be where you have some sort of process identifier. Whatever that is typically. Maybe that is an important number or something. It doesn't matter. You just have to uniquely identify the node, what that means in our system. It has to uniquely identify that node. And so if we capture the node identifier and then start presenting having a vector clock, as you sit there and think about this is going to be more complicated because then you can't do the max over that thing. Because what do you do when there's no vector for one, no value in the particular slide of the vector? You say, well, I guess I'll just have 0. That's a perfectly reasonable way of approaching it. This is really easy for small groups. Angle straight. As you get into large numbers, it's a lot harder. You know, much more complex representations of the solution space. All right, so the studio today, which is going to be 30 minutes, I'll give you one of the things not much. It says 12:25, so it's 15 minutes and 12:40. So you can just groups, people walk out there. Just look at it. Try to reason about how would you debug a log like this that only has timestamps, only has bulk time. So the idea is trying to help round the thing we're talking about while so fresh ahead you're going to talking about, which you probably do a lot more in this class. Almost exactly like 436, right? Oh, we need to kind of puzzles to think about sometimes. You'll look the opposite way. So you'll see what's returned here, you go, that's not the right value, and you have to walk backwards and go, how can we possibly have that? It's going to be received. So I'm making this. Oh, I scared enough people off it. I have no idea if I'm this, but take a look, I guess. Or, no. You might have yourself had it, I don't know. What the fuck is that me taking this class? Receive response. So like what it says, no, B at 10:02 receives from A the value of P actually was 1. So the point here is you got a message from node A saying the value here was 1. Correct. Put these clients, since these are correlating with each other, put from the other nodes, any node, put one node, or receive from one node. Well, it's just not applications yet. Don't complicate it. It's just how you reason about what you actually see on the last step. The problem is if you do this right, you're going to finish the pass through here, and you can't reason about it. That's the whole point of the exercise.
But these values be like changeable.
Right.
So this,
I pulled it does.
yeah, so this one's saying like current but current. So everything was C happened for A, I'll be but it will change for A.
It's even before A. Okay, so all you have is this log that says 10:01 A received, but it says write 1 to the PX, and at 10:02 C received the quit that says TX equals value 2.
And then after A, yes, and I'm thinking if this happened for today.
Correct. That's you're seeing back there possible path because the log time doesn't really the actual order of the events occurred.
So that make them
Concurrent. There's no causality there. If you want to add causality, people are going to say who came from, not just that log is limitation in that regard. But I wish a little bit of the information in. That doesn't really happen. And the purpose here is to see how you reason about this and start getting comfortable with that because we will get more complicated examples. It's pretty much what we're doing a lot. Saying, as I mentioned earlier, there's sometimes a little bit this is wrong. So that last thing return, you have to be walking back to figure out how that happened because that will lead you to understand what it is. There's many instances in there. And often, my training, I often spend time thinking about the order of events and where they were concurrent and what the order would have done that might have led to the result I see. And I see that and I say, okay, it's important now. But because it's not this, is it concurrent? I'm not sure. That's why I could consider them. Often these kind of problems come in packs, so you have multiples of them, that way these are running them not harder. This is one of the reasons why design upfront is so critical, because bundling the field is the nightmares. You know, I have a framework PhD. A PhD is what I'm doing for something like Amazon, which relies on Amazon in things great. And a pretty common you get a text message from somebody that says, this is down, you go figure out why. And no one can else has to see. So, no. That's why I like my next slide after goes on, right? I don't change that now. I know the word is for free, so it wasn't my imagination. It was before it came in. What's for free? I don't really care. It's nice. So next slide. I could actually look at that thing. We're interested in causality analysis. All right, so let's decide what should be out in B's return. What? You ready to because at least you pass through that. You would assume that the order of the receive was relative to the order of the send. The sender and receiver's times don't have to be correlated. This is bullshit very quick, just for walk time, you really can't quite tell. You need something for 1 second. Or, yeah, 1 second. This doesn't have to be A's head. It was just simply the A's head before. Because A doesn't record a sender, only sends when it receives them. And C and D also do the same thing. So C is, go back. So C to put a 2, it's 2, even though B got to get at 10:05. No longer B right from. Get B right from A at the same time as C send the message to the value 2. So that's why you actually get value 1 from them. This is kind of the whole point, is that you're looking at that and saying, if I interpret those as the correct order of the actual events, then it will be when. So it's order return 2, what you're doing is you're average and saying, how did I receive it here? Question no? It's received, not what's. That's the order to receive the response. So your point is that at 2, B got an answer from A. Just because you receive it out, correct? I mean, receive doesn't necessarily mean you change value. B's, if you B's client names your servers, and the others are out of sync with each other, for example. Although, I don't know what it doesn't need to be a simple example. Now, it's a little complicated. This is totally simple. So, how do we solve the problem? Because that's really the point here. I don't know. What do you need to know? Just we can start. We can say database. I mean, it's basically variable. You're complicated. You're really saying there's a request. I mean, I just like it's variable. Literally, just tell me 3 processes on variable. Right. Well, you know what receive does, correct? So that's interesting. The example is that it presumes that you know what receive means. So how about this? The put sets value. You assume that receive doesn't indicate this sets value. It indicates that you see the answer for what value is. So the first transaction, the first pair received A, B, that makes sense. Then you see that C, at the same time, received this value. A received from C the value 2, so that means that this, you know, this receive happened after this split. We see this value after this split. But here ambiguous. I think it's kind of interesting where to receive that from. But let's say received it from A. I think that's the reason it's ambiguous. If received from A, and put 1 here, I don't see the put. So that means it's different values. So that's what this here. It doesn't receive from. I'm trying to get this example. Question back there. because you're assuming the order of receipt is order of sit in, but that's not guaranteed. But it doesn't say sit in order. It's the same order of sit. It's the same thing that we answer, which is the real question here. What do I need to know? Question here. C sent a value after A. Let's say that B sent a get before any of these times. It doesn't receive a response to it until after these times. So the point is, again, we're not saying when, we're saying when to get or not when to go sent. They call and say, what's your value of X? And you say it's 3. You could change the meantime. We don't have an order in here. So what is missing from this log format? Well, how do we add clock timestamp from the sender? Then we can reason about it. Then we can see, oh, okay, it's because this was sent by A in response to doing get. You want to know when the sender sent it, because that allows you to create order for those things. You want to know when the receiver received it. And that's exactly what we use when we built logic clocks. We just use wall clock times. We use one clock counters. Is there any reason that we actually know when we use wall clock times? What is the requirement of the number clock? No. It's not counting. Our timestamps, our wall clock time is not counting. Moments when the secret here's the secret, it can change the clock back. You can move forward. It fixes the time so that it is in sync. But it actually does roll backwards. And rolling backwards immediately means that we can no longer have longevity guarantee. So in fact, that's one thing that a number clock does, is we have the wall clock time. And if you 50 times roll backwards, you're wrong. They do. It causes different problems. Recently there was a long power outage at the US National Institute of Science and Technology in Boulder, Colorado, and the clocks went off. And these are really high precision cesium clocks. And they had to actually adjust times. This is just a technique to adjust time. So this is not perfect. All right, I think that should. Since it's about, we do that here, we're going to see. So the subject is at 50 minutes, and it's due to this class. The next class we'll actually be able to short because the Department of Computer Science is scheduled something else at 1 that's 12:30. So we'll learn about 45 minutes next on the day. Yes.
So we returning the last time we received.
We're returning the last time you received it.
We returning the last time we received.
It's a very nice ambiguous log format because we don't know if that's the